In this video, we're going to take a look at fusion power. This is an alternative to fission, which is actually much more attractive than fission. Fusion has many advantages. It produces more energy, there's no radioactive waste, you have lots of fuel available, and all around a good option. The problems with fusion are currently technological problems, and we're going to look at those. The basic principle, though, is this. Two smaller hydrogen nuclei fuse together, they form a larger helium nucleus, and in the process release tremendous amounts of energy. Here's the reaction. You have hydrogen 3, which is sometimes called tritium. You have hydrogen 2, that isotope is sometimes nicknamed deuterium. They join to make helium and an extra neutron, plus the energy. The energy that is released is given to the two products, the helium and the neutron, as kinetic energy. They move really fast after the fusion. So one of the obstacles has already been solved. It was this issue about temperature. You can't produce fusion at really low temperatures. Here's the reason why. What you do to get fusion to occur is you put a bunch of hydrogens together so that they're bouncing around and colliding, and every now and then, two hydrogens will approach each other. When they approach at a low temperature, here's what happens. They get closer, they slow down, and then they go back away. Why does this happen? They're not moving very fast, and because of that, they never get very close. In other words, they never get close enough for the nuclear force to dominate. While they approach, they are being repelled by the Coulomb force. After all, this has one proton in red, and this has one proton. So those protons repel each other, and when the two hydrogens approach, if they're not going very fast, then they never overcome that repulsion. At really high temperatures, and we're talking super high, in fact, this is 10 times the temperature of the sun's core, right? And that's the temperature we need to produce fusion in our laboratories, in our power plants. So at really high temperatures, here's what happens when two hydrogens approach each other. They're bouncing around randomly, and then just by chance, two start to come head on like this. They come closer and closer, and they slow down, but then eventually, because they're moving fast enough, they form a helium atom, a helium nucleus. And one of the neutrons is ejected off. And because so much energy is released, these things are moving really fast. In this case, the hydrogens, which started out on opposite ends here and here, they were moving much faster, fast enough to basically touch. At that point, once they touch, the strong nuclear force takes over, and they no longer are being dominated by the Coulomb force. Instead of that repulsion, they feel attraction. So, in fact, we can produce temperatures of 10 times the core of the sun. But this question arises. Even if we can get something that hot, this hydrogen gas, what kind of device can possibly hold some fuel, at such a high temperature? How is that possible? The answer is we use something called a tokamak. So let's watch this video about tokamaks.
The interior of a tokamak is shaped like a donut. Here, temperatures exceeding 150 million degrees Celsius force atoms of deuterium and tritium to fuse together, forming a hot plasma. The plasma must be kept in motion in the center of the chamber and away from the walls of the vessel. This is the job of the superconducting coils that surround the tokamak.
So right there, we've seen the key already. The fusion fuel is this incredibly hot hydrogen gas. In fact, it's so hot that it becomes what we call a plasma. That just means that the electrons have separated away from the hydrogen nuclei. So this incredibly hot plasma is what you see right there. It's spinning around inside the tokamak, but it doesn't touch the walls. How is that possible? We use giant superconducting magnets. That's what these are. And the magnets, through some advanced physics, are able to confine the hot plasma inside the toroidal shape or the donut shape without touching any of the walls of the vessel.
With ITER, a new chapter in the book on fusion research will be opened.
So there it is from a cross section. The gas is entering the plasma is entering right here. It's going around and then it goes out of view and it comes back out here and it just continues cycling around in a circle. So why doesn't this technology work? This Wikipedia article actually provides a pretty good explanation. It only can be confined, that hot plasma can only be confined for just a few seconds inside one of these tokamaks. What happens after a few seconds? It's like trying to squeeze a balloon. The air always finds a place to pop out. Turbulence in the plasma has proven a major problem, causing the plasma to escape and potentially touch the walls. If the plasma escapes, then it's no longer contained and it quickly lowers in temperature. If it touches the walls, something called sputtering happens, which is where the high mass particles from the container, right, the vessel, has now mixed in with the fusion fuel, and then that lowers the temperature very quickly. So fusion can only be sustained for 3 seconds. As soon as the energy gets high, it goes away. It either escapes or it mixes with the walls, and that lowers the temperature. So these high temperatures can only be sustained for about 3 seconds at the most. So fusion has huge advantages. It doesn't produce any radioactive waste. All you have is helium and neutrons. The hydrogen fuel that we put inside the tokamak is readily available. We have so much hydrogen on the Earth. In fact, you can produce hydrogen just from ocean water using a process called electrolysis. And fusion fuel generates a tremendous amount of energy, more even than fission. What are the disadvantages? There's only one. It doesn't work yet.